All right, continuing in 7.1, we're ready for example 5, which talks about the derivatives of inverse functions. And this example is kind of like proving the theorem that we're going to have. It says we're considering a general equation y equals mx plus b, which is a line. Find the inverse and write it in the form of f inverse of x. So the first thing we do is we switch the x and the y. And then we solve it for y. And so f inverse of x, and I'm going to split this up into two pieces, x over m minus b over m, which describes a line that has a slope of 1 over m. Let me rewrite it again. That'd be 1 over mx minus b over m. Remember, b and m are numbers, so the slope of this is 1 over m. That answers part A. Part B wants us to find the derivative of the inverse. So part B says you have f inverse, the derivative of that. It would just be 1 over m, because the derivative, x is the only variable there, so 1 over m is its derivative. Which, if you'll look at the original question, the original problem, m was the slope. So this is equal to 1 over the derivative of the original. So what you're supposed to notice here is that the derivative of the function is m, and the derivative of the inverse would be the reciprocal of the derivative of the function. Part C, they want us to consider a specific case, y equals 2x minus 6, graph f and f inverse, and find the slope of each line. Okay, if I'm graphing this, and it doesn't actually ask us to find the inverse equation, but we will. This one has an intercept of negative 6 and a slope of 2. So it's going to go through those dots, which again probably all appear at the same time. And now we're supposed to find the inverse function. There's the inverse function. I can write it as a separate thing and write f inverse of x and split it up, 1/2 x plus 3. So now I'm supposed to graph that. Now I could do the same thing. I could plot the y-intercept is 3 and the slope is 1/2. However, it would be easier just to switch the dots that I've already plotted. The first dot I plotted was 0, negative 6, so the inverse would be negative 6, 0 out here. The next dot I plotted was 1, negative 4, so negative 4, 1 would be the inverse. And then the last point, let's go to the end one. We plotted 3, 0, so 0, 3. Since I really only need 3 dots to get this. And this guy's going like this. And what you're supposed to notice, again, if we draw in the y equals x line, the dotted line, it's going to go... I'm trying not to touch the graph so that you can see it. And so they are mirror images of each other. So this brings us to theorem 7.3, which says that the inverse's derivative at y sub 0, since the inverse is in y's, would be equal to 1 over the derivative of the original function at x sub 0. And this means we're talking about the point x sub 0, y sub 0. So number 6 is going to use this formula right here. It says the function f of x equals square root of x plus x squared plus 1 is 1 to 1 as long as I pick x is greater than or equal to 0. It has an inverse. Find the slope of the curve f inverse at the point 3, 1. And they've got the pictures drawn in the book. We don't necessarily need the actual picture. So what we do need is we need f prime at x, and the point in question is the point 3, 1. So f prime would be 1, that's x to the 1/2, so 1/2 x to the negative 1/2 plus 2x, which I would fix to be 1 over 2 the square root of x plus 2x. And now we have to go in reverse. We have to stick the y value in. So we evaluate it at f prime at 1, which gives me 5/2. That means that the inverse function's derivative at 3 would be 1 over f prime at 1, which is 1 over 5/2, or 2/5. The slope of the inverse function is 2/5. Notice you don't have to find the formula for it. You just have to know, you don't have to find the inverse function, but you have to know the formula to get to it. So it's kind of backwards. And you're sticking in the y value because this particular point we're trying to find the inverse function, and so you switch the x and the y, so the new x value would be 1 instead of 3. This concludes 7.1.